Today we're going to look at, this is going to be section 9-2, product and quotient rules for radicals. So we're going to use some of the laws of exponents and rules for radicals we looked at before to develop these. First one, we have some radical u times v. We know from last week that this is u times v to the 1 over n. You might recall, like, square root of 5 is the same as 5 to the 1/2. So the nth root of u times v is u times v to the 1 over n. But because of our rules of exponents, you know I can distribute this 1 over n. So this is u to the 1 over n times v to the 1 over n. And these, again, we can convert back. This is the nth root of u times the nth root of v. So this is the nth nth root of u times the nth root of v. Can I erase this? Okay. So this is the rule you have to know. That's the product rule. I guess I'll write it over here and move it over there. The quotient rule looks like this. The nth root of u over v, well, that's u over v to the 1 over n. And again, according to our rules of exponents, that's u to the 1 over n, or v to the 1 over n. So it's the nth root of u over the nth root of v. So let me write that down. Root of u over v equals the nth root of u over the nth root of v. All right, so we want to see how those two rules can help us in simplifying expressions. So here's a nice straightforward example. I have the square root of 75, and I want to simplify that. Well, I know that the square root of 75 is 25 times 3. Square root of 75, 25 times 3. And I know that 25 is a perfect square root. So this is the square root of 25. This is the square root of 3. And the square root of 25, of course, is 5. So I just end up with 5 times the square root of 3. Right? It's a nice simplification. This is using the product rule. Here's an example using the quotient rule. I have the square root of 162, the square root of 10. Well, I guess really what I have is the square root of 162 over the square root of 10. So that's the square root of 162 over the square root of 10. Then I use the fact that 162 is equal to square root of 81 times 2. And the square root of 10 is the square root of 5 times the square root of 2. Jumping the gun here. So this is the square root of 81 times the square root of 2, or the square root of 5 times the square root of 2. Well, of course, I can cancel the square root of 2 over the square root of 2. And the square root of 81 is, I hope you know, 9. So I have my answer here, 9 square root of 5. 9 over the square root of 5. This is going to come up in a minute anyway, but I just want to throw it out. Some of you may have experienced a teacher who told you that this is not okay because there's a radical in the denominator. Anyone here run into that? Okay. All right, so one shaking hand. I'm sure there's more. The idea is there's something wrong with that. Right? Let me assure you, in this class, and in my humble opinion, there's nothing wrong with that. But what that teacher would want you to do is say, all right, let's multiply this by the square root of 5 over the square root of 5. So I get rid of the radical in the denominator. I get 9 over the square root of 5. This is called rationalizing the denominator. We're going to talk about this. If we're just talking about numbers, the idea is somehow this is better than this. Yes, I think I actually have a paper on this issue where someone explains why this came about and why it doesn't make any sense anymore anyway. Right. Just in case you've run into that, I wanted to mention it. All right, let's take another example now, but this time, instead of just numbers, let's make this an algebraic expression. So we want the square root of 25x squared. Right? Well, we know we can write that as the square root of 25 is the square root of x squared. Of course, we know the square root of 25 is 5. Now, one might be inclined to write the square root of x squared as x. Most of the time, that's going to work for you. So let's think this out for a second. Let's say x was 2, right? So we have 25 times 4 is the square root of 100 equals 10. And 5 times 2 is 10. So that worked. But what if instead x was minus 2? Well, all right, let's see what happens. 25 times negative 2 squared is 100. Square root of 100 equals 10. All right. And what's 5 times negative 2? Negative 10. Well, that didn't work out somehow. We squared x, which made it positive, and then we found the positive square root of it. Right? But somehow here we end up with a negative that we shouldn't. So the correct answer is this should be the square root of x. I'm sorry, this should be the absolute value of x. I hope you can see that. So now we can see that worked out okay. This happens whenever you have a variable to an even power, like to the 4th, to the 6th, or even to the negative 2. If it's an odd power, you don't have this problem. Right? Cube root of negative 8 is just negative 2. Negatives are okay. This is an odd power. Right. Any questions so far? We're just doing mechanics here. We're learning how to simplify these expressions that have radicals in them and now variables. All right. Let's go one step more complicated. Any ideas on this? What I should break this up into? Yes?
72 squared times x cubed squared times y squared.
Mean like that?
Yeah.
Okay. It's pretty good. About 72. Any thoughts on this? I know, kind of like juggling, So I can't even catch 10, It's like numbers are kind of like that. After you've done it, practiced it for a while, you look at numbers and you just kind of see what's there. If you don't, well, let's try and break 72 up. So 72, it's even, so 2 divided into 72, that goes 3, 12, 36. 2 into 36, oh, that's 18. 2 into 18 is 9, 3 times 3. So you look at this and you look for pairs. Right? So we got 4 and 9, that's 36. It's a perfect square. 36 is a perfect square, it's 2 times 3. So where you'd like to get to, you can always go through that process, but where you'd like to get to is you just look at that and go, well, that's 36 times 2, right? Let's bring all this stuff in here. All right, so this is square root of 36 times square root of 2 times, let's work on this. X cubed, the square root of it. That's like x squared times the square root of x times the square root of y squared. And what do we got here? Well, this is 6 times the square root of 2. I'm going to leave off the absolute value signs. I'm going to show you why in just a second. This is just x, square root of x, and here, y squared and the square root of it, I will put them. So, all right, this one will line up. Yeah, that's fine. 6 square root of 2, x square root of x, absolute value y. The reason I don't have to put the absolute value sign around the x is because I've got a square root of x. That can't be negative. So it's got to be 0 or positive. So I don't have to worry about that. Y I do. If y were negative, it gets squared, and then I find the square root and it becomes positive. All right, so this isn't necessarily simpler than this, although getting that 6 out of there helps. But if we have a rational expression we want to reduce, we might want these factors separated out so we can reduce them. Let's try something with a cube root. Remembering for odd root radicals and odd powers, we don't have to worry about that negative problem, negative value problem. Cube root of 40. Now again, it'd be great if it just jumped out at you that what we could do with this to reduce it. But since we don't, we're going to factor it. So 40 is what? It's 2 times 20. And 20 is 2 times 10. And 10 is 2 times 5. Okay? So since I'm doing a cube root, now I'm looking for groups of 3. So this is cube root of 2 times 2 times 2 is 2 cubed times the cube root of 5. And this, of course, becomes just plain 2. So that's how I could simplify that. I see a problem here. My problem is written wrong. So we'll correct it. And I do that. All right, doesn't matter. So square root of 36 x squared over square root of 8. Well, now I'm gonna go through that, even though I kind of know what the square root of 36 is. 2 times 18, which is 2 times 9, which is 3 times 3. And I have my x squared. And the square root of 8 is 2 times 2 times 2. So, again, square root of 2 times 2 times the square root of 3 times 3 times the square root of x squared over square root of 2 times 2 times the square root of 2. Just cancel those. This becomes 3. This becomes the absolute value of x, and again over square root of 2. Now wait a minute. That's not what I wanted to do. Is it? No, that is what I wanted. I'm sorry. Okay. It's kind of one of those mentally challenged days here. Yes.
How come for that one you wouldn't just say like 6x?
Oh, I would actually. I was just trying to kind of use kind of the lowest common denominator here. You're right. If you see, that's what I'm trying to get at. If you see that, right? This is what you saw, right? Okay, let's go through that. Okay, so that's the square root of 6 times 6, the square root of x squared over square root of 2 times 2 times the square root of 2. So this gives me 6, absolute value of x, over 2 square root of 2, which gives me 3, absolute value of x over square root of 2. Did I get the same answer that time? I hope so. Yeah, I mean, it's kind of your level, right? If I wrote down this, right? Just kind of blink. Does anyone know what the square root of 144 is? You do. Okay, good. Right, not everybody has that in their head. I think I may even mention this in this class before. 144, it's how they used to sell pencils. You wouldn't buy 100 of them, you'd buy 144, and there's a name for that. Anyone know the name? It's a gross, yeah. Yeah. Why is it 144? Well, there's this idea of a dozen. Everybody knows what a dozen is, right? Unless you go to the baker. It's 12, and 12 times 12 is 144. It's just 12. So not everybody knows all these, you know, above 100. There's a few that are good to know. Well, obviously 100, good to know the square root of 100, that's easy. 11 squared is 121, that's a good one to know. 12 squared is 144. Now that's probably, now I'm kind of picky. 169 is 13 squared, and I can't remember 14. But I can remember 15 is 225. It's 15 squared. And 16, because I'm a programmer, and all people who be a programmer should know that 256 is 16 squared. All right. You know what a byte is? Computer byte? Computer byte, in your computer you got memory. At 8 bits. 2 times 2 times 2 times 2 is 16. 2 times 2 times 2 times 2 is 16. 16 squared is 256. That's how many numbers you can fit into a byte. Well, kind of 0 through 255. All right. Sorry, digression here. This is just, this comes under the category of what they call number sense. And you only get it by being around numbers and playing with them. And I don't expect everybody to know everything, but all right. Another example here now, a cube root with some variables. Okay, this looks a little more challenging. Well, we're going to use our quotient rule. This is the cube root of y to the fifth. And cube root of 27 times cube root of x cubed. And we might as well change this to cube root of x cubed times x squared. Anyone know what cube root of 27 is? Okay, again, this is like, you know your cubes. 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is, you know this one? 16 times 4 is 64. 5 cubed? Anybody know 5 cubed? What's 5 cubed?
125.
125. Yeah, these are good numbers to have, you know, just like you know lots of words that other people don't know. Right? Everybody has a little vocabulary, the number vocabulary. Okay, cube root of 27 is 3. Cube root of x cubed is just x. We don't have to worry about absolute value. But here now, this is the cube root of y cubed times the cube root of y squared over 3x. So what do we end up with? Just y times the cube root of y squared, which is 3x. You might also want to remember you can write the cube root of y squared as y to the 2/3 over 3x. That's another way to write it. All right. All right, so I already mentioned a minute ago this rationalizing the denominator thing. You get the square root of 2, and some teachers don't like that. So multiply it by the square root of 2 over the square root of 2, and square root of 2 times square root of 2 is 2. So you get this expression, which to me does not look better than this, but there you go. However, when you're dealing with variables, when you're dealing with x's and y's, it's sometimes a good idea to get radicals out of the denominator. So, for example, let's say you have 1 over the square root of x. Well, then it might make sense to go square root of x equals square root of x over x. Because again, sometimes it's useful not to have a root in the denominator when you have a variable. We'll see some examples of that, I'm pretty sure. All right. I guess I should add that if you're trying to rationalize a denominator and it's not a square root, it might be a little more difficult. Like if I had, say, 4 times the cube root of 9, I might have to think about that. That's 4 times cube root of 3 times 3. And what's missing to get this radical out of the denominator? Well, I need another cube root of 3. So I have to multiply that by the top and the bottom. So now I have the cube root of 3 times 3 times 3 is 27. So that's just 3. And on top I have 4 times the cube root of 3. So when you have a radical with more than a 2, sometimes you have to add more of those, whatever it is you're trying to get rid of. All right. The next thing we want to be able to do to simplify these expressions is know how to add and subtract them. So if we're lucky, we get something like this. Square root of 7 plus 5 times the square root of 7 minus 2 times the square root of 7. And we can just use the distributive property. We take out the square root of 7 as a factor. We get 1 plus 5 minus 2. What do we end up with here? 6 minus 2 is 4. We just have 4 square root of 7. The same is true if we have some kind of variable in there. So if we had 3 times the cube root of x plus 2 times the cube root of x plus square root of x minus 8 square root of x. Well, these radicals are different, so we're not going to be able to mix them. But we still can combine these groups here. So we have 3 plus 2, there's the cube root of x. And here we have 1 minus 8, there's the square root of x. So we have 5, 3 square root of x, minus 7 square root of x. So we can combine like radicals. Now, when we're trying to do this, we might not get something nice like this, where it kind of tells you right offhand that, you know, these things are the same. So you might see something like this. Square root of 45 x plus 3 times square root of 20 x. Okay, it might not be obvious at first that we could simplify this any, but we take a look here and what do we got? We've got square root of 9 times 5x, and here we have 3 times the square root of 4 times 5x. And we see, oh, that's a square, and that's a square. So skipping a few lines here, square root of 9 is 3 times the square root of 5x. And when I take this 4 out, it becomes 2. 2 times 3 is 6. The square root of 5x. Oh, and now what's under the radical is the same, so this I can just add 3 and the 6. 9 times the square root of 5x. So again, you have to kind of be a little flexible and a little creative. You have to juggle a little. Here's another one like this, only maybe a little more complicated. 6 over the square root of 24 x to the 4th minus 3 square root of 54 x to the 4th equals what? Well, okay, so I look at my x to the 4th. Well, that's nice. I have a common denominator already. That helps a lot. When I take x to the 4th out of the square root, again, it's going to be the absolute value, but it's going to be x squared, so I don't have to worry about it. X squared already has to be positive. So I have 6 times the square root of 24 minus 3 times the square root of 54 over x squared. So that helped. Now again, I'm going to look here. This is 6 times the square root of what? 4 times 6 minus 3 times the square root of 54. Anybody can factor 54. 9 times 6. And again, now I've got a 4 here, so I know that I can take it out as a 2. 12 times the square root of 6 minus, I've got a 9 here, taking it out as a 3. 3 minus 9 square root of 6 over x squared. And lo and behold, this is nice and simple. 12 minus 9 is 3 square root of x over x squared. All right, so again, another level of complication. Sometimes when you have something like this, you do have to rationalize a denominator to get anywhere. All right, let's look at this example. It's kind of hard to add apples and oranges here, but I can rationalize this denominator, which may help. So this is the square root of 7 minus 5 over the square root of 7 times square root of 7 over the square root of 7. Right. Square root of 7 minus down below, now I just have 7. And on top I have 5 square root of 7. So this is, I can take out the square root of 7 here. And I get 1 minus 5/7. Well, 1 minus 5/7 I can do in my head. That's just 2/7, right? So 2 square root of 7 over 7. I'm done. All right. That was a lot. That was definitely a lot. The only way you're going to get comfortable with these is if you do the homework, practice it a little. Again, if you have questions, you should bring them in. Come to my office hours. There's one more trick. And this trick is just, it shows up from here, every math class, just about every math class and beyond. It's a really good trick. And it shows up in, when we're using radicals, but it shows up in other places too. I think we have enough time to go over it nice and clearly. Before we do, I'm going to remind you of the key, kind of the key piece of wisdom that makes this possible. Remember when we were factoring, I told you there were some important patterns. And one of the most important patterns is a plus b times a minus b equals, somebody tell me. Do you have to go?
Yes.
Okay. Someone want to tell me what a plus b times a minus b is? You really want this to just roll off your tongue. I mean, you can FOIL it and you'll find out. Yes?
0?
No, but good try. Let's FOIL it and just, right? Firsts, a squared, lasts, minus b squared, inner, ba, outer, minus ab, which is the same as ba. These cancel. A squared minus b squared. And you want to know it both ways. When you see, like, to see x squared minus 4, you should think x plus 2, x minus 2. And when you see x minus 2 times x plus 2, you should think x squared minus 4. Really important pattern. You know, get yourself one of those wood-burning things and put it on the side of your head, or don't do that. That would be good. You get one of those haircuts, you know, buzz cuts, where you put something on the side of your head. That's only going to help your partner while you're, you know, your neighbor while during the exam, but just your being mirror. Okay, how does this come in? Let's see how this comes in. Have a problem here. Square root of 3 over 1 minus square root of 5. What can I do with that? Well, in this case, I go along with whoever, you know, whoever wants to rationalize the denominator. We don't want a radical like this in the denominator. So let's get rid of it using this pattern. On the bottom, we're going to write 1 plus the square root of 5. Well, of course, we have to multiply the top by 1 times the square root of 5, because that's 1. Now, what do we get here? pattern tells us this is 1 squared minus the square root of 5 squared, which is just 5. Up here, we have square root of 3 plus square root of 3 times square root of 5, square root of 15. And what do we have here? Minus 4. I don't know. Maybe we want to keep the square root of 3 out. 1 plus square root of 5. Doesn't matter. But I've gotten rid of that radical in the denominator. Now, with numbers, this is kind of moderately important. It's not that important. Moderately important. But with variables, it can be the answer to your dream. Say I have something like this. 1, the square root of x minus the square root of x plus 1. Well, you don't get much uglier than that. But I want to get these radicals out of the denominator. So I think of my pattern here. There's my a minus b. And I can get them both squared by multiplying by a plus b, which in this case is square root of x plus the square root of x plus 1. Okay, so what do I get in the basement here? I'm going to get square root of x squared minus square root of x plus 1 squared. That's my a squared minus b squared. Well, square root of x squared is x. Actually, it's kind of an absolute value of x, but we're just, for the moment, we're just going to make believe these are all positive numbers. We don't have to deal with that. Minus square root of x plus 1 squared. That's x plus 1. And I just have this thing on top. Well, square root of x minus x plus 1. The x's go out, and I'm left with minus 1. And if you like, I can bring the minus 1 up top. 1, which just gives me minus square root of x minus square root of x plus 1. So I took this kind of ugly thing, and now I don't even have a fraction anymore. Now, I don't know what I'm going to do with this next, but at least, it's something I can handle. So, okay, I think that's what I got for today. Any questions? Again, we're just kind of manipulating these radicals, getting a little practice with that. Yes.
So this lesson we just covered about like radicals, that's not going to be on the midterm on Tuesday.
Nothing today or Thursday will be on the midterm.
Okay, I just
It
wanted
can be on the final.
yeah, that's what I'm
The homework isn't due till next Thursday, so
On the-
worry about the midterm and then, have time to practice this on Tuesday and Wednesday.
saying. All right, so
All right, thank you.